Welcome back to our video module on dynamics. Today we're going to do a little bit more exploration to try to get a good feel of what's happening with these various forces that we keep applying to our cart. And what I'm going to do is I'm going to make a little chart here. And this chart is going to be our record of position, acceleration, and velocity. Oops, sorry. Acceleration as functions of time. And we're going to follow the cart and see what happens with various forces. The first force we're going to look at is F equals 0. This, of course, is roughly akin to just watching the cart go by over time. And what I've done is even gone as far as in gray showing us solving the differential equation that addresses this force. As you can see, the velocity with respect to time is just v naught. It's a constant. We'd expect that. There's nothing changing it. And the position right here, it starts at some x naught and increases linearly with time. So let's see if we can draw that out here. This is really basic stuff. We start off with, let's say, our velocity is v naught. And it's going to, it's not going to increase. It's going to go nice and steady. Our acceleration is going to stay right at 0. We'll put it on there just so you can see it. And finally, our position is going to start off at x naught, and it's going to increase maybe something like this at some slope based on v naught. Next, I'd like to take a look and see what happens if the force is a constant. This is roughly akin to what you've probably seen in physics, where you're going to apply a force to some mass, and we're going to track its position as a function of time. There too, in yellow, you can find the derivation of its velocity as a function of time and its position as a function of time right here. Its acceleration, as you can tell, is pretty simple. So I'm going to take a shortcut on these equations because the constants are going to depend on your initial conditions. They're going to depend on all sorts of things. So we're going to show the general function without sweating the constants in the graph. That said, when the force is a constant, we know the acceleration is some negative constant. We'll say negative c1, and we'd expect it to be negative because, as a reminder, let's draw our coordinate frame. The acceleration is always going to be going in the negative direction. The velocity is going to be the initial velocity minus some constant times time. And finally, its position is going to be the original position plus v naught t plus 1/2 c1 t squared, and that's actually a negative c1 t squared. And that would look like this. Our acceleration is going to be some sort of negative constant. Our velocity is going to be the initial velocity, and then it's going to decrease linearly with time. Finally, our position, right off the bat, it's going to be tangent to this line. It's going to be going in that direction, and then it's going to slow down until, hopefully I got that right, until about right here where the velocity is now 0, and then it's going to decrease back to the original position. And this is your simple parabolic motion. Next, let's take a look at this equation right here. This, as you recall, is our viscous drag, and we have our velocity right here, our position right here, and the acceleration is going to be the derivative of our velocity. Let's go ahead and graph the sense of that equation. So in this case, and what was that, red? F equals some constant times the velocity. And in this case, the position is some x naught plus some constant times e to the negative, and we'll say constant 2t, c1, e to the negative c2t. It really goes in that sense. And the velocity is v naught times e to the negative c2t. And finally, the acceleration is some constant, we'll call it c3 e to the negative c2t. So we can see that we have a lot of exponential decay here. For acceleration, that exponential decay means that we're going to have a pretty high negative acceleration. It's going to decrease towards 0. Our velocity is going to start off at v0 and decrease like that. And finally, our position is going to start off right here, and it will start off tangent, and it's going to kind of hit some sort of limit. It's just going to go like that and approach a position. It's never going to want to get less because the force is always fighting the velocity. There's no way to make that velocity go negative. Finally, let's take a look at the white. This is F equals negative CV squared. This is quadratic drag. This is the type of force you're going to see if there's very high velocity, if there's a very high velocity object going through air or some sort of fluid. The velocity is right here. Our position is right here. And if we graph those, we'll go ahead and graph those in white. Right there. We see F equals CV squared. The acceleration is negative c1 times some sort of inverse square. So 1 over, we'll say c2 t squared. The velocity is going to decrease starting off with v0, and that's a 1 over, we'll say c3 t. And finally, the position, we're going to have the original position plus, we'll say some constant, c4 times the natural log of t. So what does this look like? Let's start off with the acceleration. It's going to be pretty high at first, and then we're going to see it decrease rather quickly. Go like this, 1 over t squared. The velocity in the same way is going to be a 1 over t, 1 over x, so it'll look something like that. And finally, the position as a function of time, as always, it's going to start off with this original velocity. It'll be tangent to this line, but then we see something that decreases. But interestingly, over time, unlike the red, unlike our viscous drag, it keeps on increasing. It keeps on increasing, the position keeps increasing. Finally, let's take a look at what happens with our green. That's our negative sine omega t. Here we have our position. Here we have, here we have our velocity. Here we have our position. We could take the derivative to find the acceleration. And if we go back up here, we'll have to come down a little bit to be able to graph it. We have F equals F sine omega t. And here the acceleration equals some constant times sine omega t, and that one should be pretty obvious to you. The velocity is going to be v0 plus some constant cosine omega t. And finally, our position is going to be x0 plus c3t plus c4 sine omega t. Now let's take a look really closely at what happens with the sinusoidal force. First, our acceleration is going to first start off being negative as soon as that force is applied, and then it's going to be oscillating about 0. Now before we get into velocity and position, let's go ahead and pull lines down here so that we can track this together to make sure we know what's happening. So the first one was at the minimum acceleration. This is where the acceleration is 0. And finally, we have one here that's the maximum acceleration. So if we take a look at, we should make sure our sign is correct here. If we take a look at what's going on in our equation below, we see that the actual velocity will vary like this. So you can see here, the velocity is at its original amount. It starts decreasing right away, and it hits its minimum when the acceleration is at 0. Then as the acceleration increases, we see it coming back up So it is basically following this equation, or rather the derivation that we saw earlier. Finally, we see the position will look something like this. Now let's work our way back and see if we can understand what's happening in all these situations. First, with the forced sine function, we see that the acceleration is starting off pushing everything in the negative direction. As a result, the velocity is fluctuating. And you can see the velocity keeps on getting negative. And based on the constants we chose, the velocity may or may not become fully negative. Then it works its way back up to exactly what the original velocity was in the first place. Now, if we take a look at that, we see that the average velocity is right around here. That means that when we look at our position, when we get to, like right here, if we were to extend this line and extend this line, we'd see that the position isn't quite there. Moreover, if we were to track the average of what's happening, the average velocity, we'd see that it's at a lower slope. So the position is going to be less long term than it is if there weren't that oscillating force. And that's something that you could expect. The next thing is our quadratic drag. What's happening right here? We initially start off with a high acceleration pushing really hard against that cart. As a result, the initial velocity is going to drop off really quickly, and our position, you can see our position is right here, ends up being less than had we not interfered. And we saw the interesting effect that for some reason this position just keeps on increasing over time. In red, we saw viscous drag. This is something we see fairly often. And we see the acceleration high at first and then dropping off. Not quite as much as quadratic drag, but it still has a big influence. And then we see that reflected in the velocity and likewise the position. However, the position for viscous drag does end up hitting some limit. Finally, we have force as a constant. This is similar to what you probably have seen before, where we have a nice even acceleration. We have a linear velocity, and then we have a position as a function of time in the form of a quadratic. The last thing, there is f equals 0, which should be a pretty simple graph to follow and understand. I hope that our time evaluating position, velocity, and acceleration as functions of time amongst all these different types of forces gives you a better intuitive feel of how masses respond to varying forces. I look forward to seeing you in our next video module when we start to explore energy.